In the last few years, you have seen many companies are interested in developing humanoid or human-like robots. The primary incentive for these companies is the promise of a humanoid robot being general purpose. That is, you can have a single robot set to accomplish a diverse set of physical tasks, just like a human. You can have the robot working in factories and in our homes. Now, all these jobs that we want the humanoid to take on require adeptly interacting with a diverse set of objects and in various ways. This is only possible with the dexterity offered with a multi-fingered hand. But multi-fingered hands are challenging. They require multiple disciplines to come together. Hardware, sensing, control, just to name a few. Today, I want to take you all on a journey on how we may be able to achieve dexterous skills with a robotic hand. But let's forget robots for a moment. Let's consider dexterity in humans. Imagine that you're trying to repair your car. Imagine that you're trying to route a cable through a hole. When you do this, you use your fine motor skills, combining various modes of sensing to actuate your muscles and then your joints. Now, if you think carefully about what happens, you realize two things. One, the complexity, the sheer complexity of the finger movement involved. And two, tactile sensing, that is, the ability to perceive touch from our fingertips, is critical. This is in fact reflected in the sensory and motor nervous system of our body. These homunculi show the body in proportion to the number of sensory and motor nerves present in them. As you can see, the human hand is the largest from both these perspectives. We also take a long time to learn dexterous skills. In fact, many developmental studies show that children learn the ability to speak well before they learn the ability to use their hands dexterously. For example, to write. My point is this: dexterous skills are challenging. It takes, even for humans, even though it appears simple, it takes a long time for us to learn. So how then can we bring such dexterity to human hands, to robotic hands? This is a question I began working on when I started my PhD. We simplified the problem and focused on working on a specific task, finger gating dexterity, where the goal is to reorient the object in hand via finger gating. While this skill is narrower in scope, this retained some of the key elements of general purpose dexterity. It required manipulating the object while making and breaking contact, and two, it requires using tactile sensing to keep the object in a secure grasp. Then the next thing we did was build a 5-fingered hand, just like humans, and then equip it with tactile sensing. These tactile sensors, which we developed in our lab, report both contact position and contact force. So now that we have a robotic hand that is similar to a human hand, how can we achieve the finger gating dexterity that we are looking after now? A common and increasingly popular approach these days to train a robot is to use a recipe called sensory motor learning. In this approach, given a paired data of sensor output and robot actions, we train a neural network to map the sensor output to the robot actions. Teleoperation, where a human guides a robot, is a common way to collect such data. However, this is not always easy. In fact, data is scarce in robotics for this very reason. This is why you may have heard of the phrase, robotics has a data problem. In fact, when it comes to learning multi-finger dexterity, this data scarcity goes to an extreme. The problem is teleoperation is just not suited for this task. It is not possible to collect good demonstrations for multi-finger dexterity. While it is easy to map the joint motion of your human finger to that of the robotic hand, it is very challenging to map the tactile sensing information back to the robotic hand, back to the human hand. Remember, tactile sensing is critical. This prevents us from collecting effective demonstrations and creates the data scarcity. In fact, this data scarcity is what sets multi-finger dexterity apart from the rest of robotics. To address this, we turn to simulation. In a simulated environment, after a bit of research, we developed algorithms, search algorithms, that allow us to collect data in an efficient manner. And then we use this data towards learning finger gating dexterity for some really challenging objects. We'll train a neural network to act as a controller to achieve the finger gating dexterity for a cuboid and for L-shaped object. Now, through further simulation of thousands of simulations in parallel, which is about an equivalent of a year of worth of training in robot time, we also achieved robot simulations we also achieved controllers to be robust enough to be deployed on the real hand. You may notice that the finger makes multiple attempts at making contact until it succeeds, demonstrating the robustness of our finger gating controllers. Now, you may think that we did this for fun, then you're absolutely right, but it also underlies an important point. We are able to achieve finger gating dexterity even in the dark using the sense of touch, just like humans. In fact, this robotic hand was considered as one of the best inventions of the year 2023 by Times Magazine. Great. Now that we have achieved the finger gating dexterity that we were looking for, what's next? What we are really interested is the diverse dexterous skills that would allow for a general purpose robotic humanoid robot. How can we get there? We could continue to leverage simulation and scale it up. We could collect data for diverse tasks that we are interested in. This is certainly a valid approach to take. However, I think there is a vastly better alternative. It requires a major shift in perspective on what data to use, but I believe it has massive potential and they will result in an inflection point towards achieving a large number of diverse dexterous skills. I propose that we equip our human hand with tactile sensing similar to that of the robotic hand. There have been lots of tactile gloves, amazing tactile gloves that are being developed recently, so this is certainly feasible. Then we collect data while the human is performing a dexterous task, and then leverage this data towards training the neural networks like before. Now, besides the diverse variety of data that we will be able to collect and the rich data that we will be able to collect, the low-cost nature of this setup allows us to scale effectively, resulting in lots of data being collected. This is going to be very valuable in learning a diverse set of dexterous skills. But the primary reason I believe in this approach is that instead of learning human dexterity from scratch, we take a shortcut. We map human dexterity to robot dexterity. I think this shift in perspective is critical. If there is one message that I want you to remember today, then it is this: human data may be key to human level dexterity. I think this shift in perspective will launch us into a world of humanoids with highly dexterous human level dexterity that will allow us and help us in various ways. We may have a humanoid robot manning a space station. We may have it to work in very hazardous lab environments, conducting research. We could use it to work in factories and in assembly lines. And eventually, I hope that we'll have a humanoid robot dexterous enough to be able to cook for us, clean for us, and then do the laundry for us. Thank you.